So we'll begin just with a quick recap of last time. So last time, very quickly, we had started the course with a motivational discussion of Empedocles. And so now, throughout the rest of the course, we're going to be trying to live Empedocles' dream and build up a predictive theory directly from our empirical observations. The formal material of the course then begins by looking at the basic building blocks following Empedocles' basic program. We began with a little bit of scientific background that we need for our discussions, namely the existence of atoms and the evidence that comes to us from electrochemistry. And then where we really began was with our discussion of electrons. How do we know that electrons are one of our key constituents of matter? Now, the discovery of the electron then we discussed through J.J. Thomson's famous cathode ray tube experiment published in 1897. I'll just give a very quick recap of some of the key mathematical steps that we can reuse a little bit later on in today's lecture. So just as a quick review, you remember the apparatus has some large large voltage that's used to create some cathode rays that then are collimated into a beam that travels down a vacuum tube, right, a cathode ray tube, which is coated with some phosphorus coating so we can see where the beam lands, and things are collimated at the beginning of the experiment so that the beam goes straight through. The interesting part then when we probe the nature of the beams is to expose them to an electric field through a known parallel plate capacitor of a known geometry and a known voltage, so we know we are applying a straight downward electric field, and we know the length of these plates. The beam travels through there. The objects making up the beam then accelerate actually in an upward direction, so they are negatively charged. They emerge from there with some upward direction of travel. The experiment is laid out so that this deflection occurs early on in the beam, in the history of the beam, so that actually most of this angle of deflection is made up from the fact that we've changed the direction of travel of the particles. Now, the mathematical analysis for this was a simple momentum analysis. We looked at the total momentum of the emerging particles, which was their initial momentum, which was this parallel momentum, which is the mass of the particles times their known velocity, which was determined by using a magnetic field. And I refer you to the previous lecture for the details on that. Then we reasoned, of course, that the particles then are feeling this upward force, so they pick up also a perpendicular momentum component now. The amount of momentum change is always the force times the time over which the force has been applied. The force is the charge times the known electric field, this unknown charge that we're trying to find, times the amount of time spent experiencing that force. Now that force is only in this portion of the beam, and the time they spend in this portion as we travel through the capacitor is the length of the capacitor L divided by the known velocity of the particles. Finally, then, we can make a determination of our deflection angle theta. The tangent of theta, then, is the opposite over the adjacent side. We substitute in our quantities. On top, we have QEL. And then in the denominator, we have one factor of V, two factors of V, and a factor of M for an mv squared. Now we can solve for the charge-to-mass ratio of the electron in terms of purely experimentally known quantities. Namely, we can just solve for Q over M, and we get V squared over EL tan theta. Velocity is known, we know the electric field, and we know the geometry of our capacitor, and we can measure this angle. And the value that Thomson found was really fascinating. It's huge, about 176 billion coulombs per kilogram. Why that was so intriguing, actually, is that if you compare that charge-to-mass ratio of the charge-to-mass ratio of the lightest atom, the hydrogen atom, in a combination like so, when we take that ratio of ratios, and if we assume that the charges that are emitted in here are the same charge on the hydrogen ion, so that this ratio becomes 1, we get a direct measure of the mass ratio. And it's huge. It's about 1800. This then led Thomson finally to propose a model for the atom. The reasoning being this positive charge in the atom seems to be so huge, so much huger than the electrons. His model basically is that the atom consists of some positive part of a constant charge density of the total amount of charge Q divided by volume, which will be constant charge density throughout, and then the electrons are tiny little points distributed somehow or other throughout the sphere, I should point out that this sphere has some radius capital R, which was not yet known because they did not yet know the size of the atom. So that's what we had covered last time.